Hey kids, we are back talking about volumes of a solid figure with known cross sections, but this time we're going to be going perpendicular to the y-axis, which means, that's right, dy. And the reason that's important is because if you think about any sort of solid maybe that you're familiar with, like a cone, for example, if you slice it in one direction, if you take a section parallel to the base, you get circles. Those cross sections are always circles. If you were to slice it vertically and take cross sections, those would be in the shapes of triangles. So it really matters in which direction you're taking these cross sections. And so if they're specifying that, we know we have squares when we go perpendicular to the y-axis, that's really the way we're forced to do it, because I don't know what cross sections I might get from doing it with respect to x. So you kind of have to go with what they give you. So that is just a good rule of thumb here, that if it's perpendicular to the y-axis, then you're doing dy. Okay, so number one, volume of a solid whose base is the region bound by y equals the square root of x. Nicely graphed right there for you. You're welcome. Also, the other boundaries are the x-axis and the line x equals 9. So x equals 9 would be that vertical line right here. And so this is the region where we're kind of talking about here. That's the region that's the base of a solid. And we're going to take cross sections perpendicular to the y-axis, and if they are squares, we want to find the volume of the resulting shape. So one thing, of course, it's not given flat out where these intersections are. So if you really want to say, well, where does x equals 9 intersect this, then you're really saying when x is 9, I mean, it's kind of stupid. You're just plugging, 9 in for x. And of course, you're getting 3, which is this point right here. But still, wasn't given, so it's good to represent that. Now the difference here, just like when we were doing area and going, with the y-axis, is that now you are talking about taking sections or slices in this direction. So regardless of where you take that slice, here would be a big slice, here would be a little slice, but that distance is always going to be described as the difference between these x values at this spot, or specifically the difference between 9, since this x value, this boundary is not changing, and whatever this x coordinate is on the curve. Now that is changing as you go along, so the difference between 9 and this x value versus 9 and this x value. Notice it's horizontal distance, so the y coordinate is kind of irrelevant. So one thing you definitely want to do is to take that equation and solve it for x. You want it to be in terms of y, so you want an equation that says x equals whatever. So that's, easy enough to do. You get x equals y squared, and that is the same curve, but now solved for x. So regardless of where you're at on here, the x coordinate would always be y squared. Okay. So now, and of course the x value here is always 9. So now to describe that slice, which is the key to all these problems regardless of which kind of cross section you're doing, hopefully you can kind of see that distance is always going to be the difference between 9 and the curve, which is y squared. So this is going to be 9 minus y squared. That's what the x value is, right? The x is 9 and the x is y squared. And that horizontal difference, distance is always right minus left to ensure a positive quantity. Okay, so now finding that volume, you might not need the 3D picture of what you're dealing with. But if you like to sort of visualize, again, since it's kind of new, here's the 3D, or my attempts at drawing the 3D. And when you go horizontally, a little section, that means there is a square that's standing up. And when you go with a bigger section here, a bigger slice means a bigger side so a bigger square. And of course here would be sort of the biggest slice, and that would be sort of the biggest square. So maybe you can picture it'd be kind of a dome type thing that would be getting smaller and smaller as you get to this upper boundary. But the big idea, remember, is that whatever cross-section you're dealing with, you just need to describe its area. And the area of a square is always side squared. What is the side of each one of these squares? That's that horizontal distance. So for each one of these squares, the area is 9 minus y squared squared, because that represents the side. And so if that is the area of each one of these, or any particular one of them, we get the total, all of them compressed together, giving you that volume by integrating. So the volume will be integrating that area, 9 minus y squared squared dy. And since you're doing it in y values, we need to know, well, what are the boundaries in terms of y of this region. And so this region goes from a y value of 0 to a y value of 3, which is why I guess we needed that 3. So going from 0 to 3. This you could do by hand. You just square it out and integrate by hand. You want to brush up on that? Be my guest. I'm going to go to the old calculator. Little math 9 action, going from 0 to 3. In here I'm going to add my own set of parentheses because I'm going to square that. 9 minus, and remember you're just typing x squared, all with respect to x. And we have 129.6 on the dot. 129.6. Pretty cool, right? And once you get that idea down, if you can do one of these, then the rest are pretty fast. You've done sort of the hard work. You found the boundaries. You've described the key distance, which is used for every type of cross section. So a semicircle. Again, if you've only been doing this a very short period of time, so it doesn't hurt to visualize why we do this. But there's the region, and this time when you take that slice, remember a semicircle, this slice, this distance represents the diameter on that semicircle. It's kind of standing up here, so bigger slice, bigger diameter, that kind of thing. So the area of any semicircle is always pi r squared over 2, or pi over 2 r squared. And just keep in mind that for this, the radius is 9 minus y squared divided by 2, because that 9 minus y squared is the diameter of each semicircle. So 9 minus y squared over 2, that being squared, times pi over 2 will give you the area. And so our volume, same boundaries, 0 to 3, of that, pi over 2, 9 minus y squared over 2 squared dy. And that is just fine if you want to type that in, or if you remember what we did the other day, if you feel comfortable, you can not only factor out the pi over 2, but you could factor out this denominator, which always comes from dividing your diameter by 2 to get the radius. 2 squared is 4, and so factoring out a fourth along with pi over 2 really gives you pi over 8. And if you are able to just launch right into setting this up without writing this first one, that's totally fine. You clearly know what's going on. You can just land on this, and there you go. And that kind of makes things nice, because that right there is the integral we just calculated, which is still on the screen. So I could just take that and multiply by pi over 8. Or even if I wanted the exact value, I would just make a fraction out of it, leave it in terms of pi. But we have 50.894 or 50.893 if you like to truncate. And there we go. As we've noted before, that makes it significantly less than the squares, because when we saw those solids, they're a lot shorter when you use semicircles than if you use squares. They're a lot taller, which means more volume. Only reason I say that is because if you get a bigger answer, maybe you can catch yourself and say, I did something silly. I typed in a wrong digit or something. So, new type of section here. No big deal, same goal. Isosceles right triangles with one leg in the base of the region. Okay, so an isosceles right triangle, you all remember from your glorious days of geometry, is a 45, 45, 90 triangle. That's not really relevant here, but the good thing is that the base and the height are the same. Those legs are the base and the height. So, if you want to call that any letter, the area is going to be 1/2 of b times b, or b squared. And for this same region, that slice, that distance, is the leg of the triangle. So it's like a right triangle standing up that way, or I suppose I could have made it standing up that way, but that wouldn't change the area of it. This is a pretty poor rendering there, but you get the idea, hopefully, that that key distance that we keep using represents the leg of one of these right triangles. So the area of each one of these triangles is 1/2 of that base of 9 minus y squared squared. Okay, just a little readjustment here, sorry. And therefore, our volume is going to be that definite integral from 0 to 3 of 1/2 9 minus y squared squared dy. And if you like, hey, this is just the same integral we've seen now, except with a 1/2 that could be factored out. So I could just bring that 129.6 back, divide it by 2, and you've got exactly 64.8. Okay, so you see most of the legwork is done when you set those things up. You get the boundaries, you're comfortable, you describe the curve the way you want, and you can describe that key distance of whichever direction you're taking a section in. And once you get that, it's just a matter of, hey, using it properly to describe the area of whatever type of cross-section you have. Okay, so that's a good example of all three. I'm going to put up another example if you want to see a second example of just two new kinds of curves, one being a natural log graph, and maybe that makes it a little more challenging. But right there you have the basics, so hopefully that helps, and watch example 2 if you like.